Okay, so this is the answer booklet for 2.3.2, diagnosis and treatment. The first question then is on types of radiation. Draw one line from each of the named radiations to the correct description. So, first one, alpha radiation, and it is our helium nuclei. It contains 2 protons and 2 neutrons. Beta radiation then is a high energy electrons, and our gamma radiation is our electromagnetic wave. A laboratory has 3 different radioactive sources that are not labelled. It is known that one of the sources emits only alpha radiation. Another of the sources emits only beta radiation. The third source emits both beta and alpha radiation. Only the following apparatus is available. Explain how the apparatus can be used to collect data and how the data can be analysed to identify the 3 sources. So the first thing we need to do is measure the background radiation of the room for 2 minutes. Using tongs, hold a source close to the GM tube and record the count rate. So to see how much radiation is given off. Then we've got to place a piece of paper between the source and the GM tube and record the count rate. We would then repeat for the other equipment. If the count rate drops when paper is placed between the GM tube and the source, we know it emits alpha radiation because paper stops alpha radiation. Second question, half-life. Put ticks in the boxes that correctly give the meaning of half-life of a radioactive substance. So we're looking for the time taken for the number of undecayed particles to half, and the time taken for the count rate to half. Then we've got the graph shows the decay curve for the radioactive substance. Use information from the graph on page 6 to write down the count rate after 100 days. So if I zoom in, after 100 days, I would go up and then across, which would give me a count rate of 400. Then write down the half-life of this radioactive substance. So the half-life is a time taken for it to half. So starts at 800, half down to 400, and again I'm going across and I end up with the 100 days. Then it says write the time it would take for the count rate to fall from 50 to 25 counts a minute. With that then, again, if the count rate starts at 50, it would half at 25 counts, so that would be a half-life, so it would be 100 days again. And next question, draw a decay curve on the grid below for a radioactive substance that has a starting count rate of 800 counts and a shorter half-life than the one below. So our line just needs to be much steeper, which you can see. Ooh, next question. Charlotte is pregnant, just had her 20-week scan. The image of her baby is shown below. The sentences below describe how the image is formed and underline the correct word in each bracket in the following paragraph. The image of the baby is formed using ultrasound. This technique uses high-frequency sound waves for the safe monitoring of the baby during development. Explain why ultrasound is used for this type of scan instead of x-rays. Because it's safe on the baby, because there's no radiation emitted. Name one other medical use of ultrasounds. They can diagnose diseases, not just look at the development of a baby or a fetus. Question 3, still on scans. Huntington's is an inherited genetic disease caused by a dominant allele and is not usually diagnosed until 35 to 45 years of age. The diagnosis is usually confirmed by genetic testing and a CAT scan. Give 3 reasons why a CAT scan is used in the diagnosis of Huntington's. Because we can get multiple images, we get 3D images, and it's non-invasive. For drug testing, fluoride is a medical drug that caused unexpected damage to the fetuses in the 1950s and 60s. It was used for easing morning sickness in pregnant women, although it had not been fully tested. As a result of the damage to fetuses, the drug was banned. Drug testing was also made more thorough. The Thalidomide has since been used as a treatment for bone cancer. However, its use is heavily regulated to prevent a repeat of the problems it caused last century. With thalidomide came the widespread recognition that differences in sensitivity to drugs between species required consideration. Many scientists report that animals are good predictors of how humans will respond to drugs, and that current testing procedures would have identified the dangers of thalidomide and the side effects that would have been avoided. Despite this, there is evidence that animal tests cannot predict how humans will respond to a drug. In 1990, 6 different drugs were trialled in humans and in animals. The results showed that animals and humans had 22 common side effects, and there are 48 side effects in animals which did not occur in humans. There were also 20 side effects in humans that did not occur in animals. The sensitivity of animal tests is calculated using a formula. So we have the sensitivity is the true positives divided by the true positives divided by the false negatives times 100 or plus. Calculate the sensitivity of the animal test in the trial carried out in 1990. So the true positives were 22, which we can see here, and our false negatives were 20 from the bottom. So my 22 divided by 22 plus 20 equals 52.4%. Use only the information in the passage to answer the following questions. Evaluate arguments for and against the use of animals in drug testing. So it said reasons for, we can test for side effects, and against is that the animals may not respond the same way as humans. One positive outcome on the development of new drugs, we have more thorough testing thanks to that. And state why the ban on thalidomide was removed is because it was used to treat bone cancer. A class of students were using dice to model radioactive decay. There were 8 groups of students. Each group of students had 50 dice. The 50 dice were rolled. Any that landed with a 6 facing upwards were removed. The remaining dice were counted. The remaining dice were rolled again and again, taking away the 6s each time. The table shows the results from one group and from the whole class. Each group results were added together to give the class results. Give one reason why the bigger sample size makes the data more repeatable. And the answer is because it reduces anomalies. The graph shows part of the data from the whole class. Plot the remaining data and draw a suitable line. So you've got 3 marks then, 2 for plotting your points correctly on the graph and for drawing a nice curve with a single pen line. The half-life for this model decay is the number of rolls needed for the number of dice to half. Use the class results in the table on page 10 to estimate the half-life. The answer is 4. Now use the graph to find the half-life showed the method you used. So we started at 400 dice, half it to 200, and we go across and I go down and I end up with an answer of 3.75 rolls. Suggest why it's better to use the graph and the table to estimate half-life, because we're more precise. Instead of just saying around 4 rolls, it was 3.75. Use the graph to find how many rolls it took for the number of dice to fall to a quarter of the original value. So we started at 400, which you can see if I zoom in slightly. I'm going to get to a quarter. So it's our half at 200, we half it again. So again, I've done the exact same thing. Go across and down. On average, it would take 7.5 rolls. Let me just zoom that back out. And then that is our 2 half-lives. An experiment was carried out to obtain similar data using the radioactive isotope, which is a beta emitter. The initial count rate was measured to be 80 counts per second. After 210 seconds, the count rate had dropped to 10 counts per second. So find the half-life of our protactinium-234. So I have my 210 divided by 3 gives me 70 seconds. Calculate how long it would take for the count rate to drop from 80 to 2.5 counts per second. So using the Timothy table, you can see here we've got our number of half-lives, our time, and then our count rate. Okay, so we start at 0 for our number of half-lives and our time, and we know it takes 70 seconds, so I'm going to go up every 70 seconds. So 70, 140, 210, 280, 350. The number of half-lives, 0, 1, 2, 3, 4, 5. We can continue going up, and the count rate has to get to 2.5. So I have 80 in one half-life at half to 40, in a second half-life at half to 20, and I keep going until I reach 2.5. And then it's 5 half-life. The time it's taken 350 seconds. And then state the unit of radioactive source, and it's our BQ.